So good morning, everybody, and welcome to our distinguished seminar this morning. And well, it's my honor and pleasure to introduce Professor Jack Dongarra. I remember growing up, going to grad school and being introduced to parallel computing and HPC through Jack's work, and being tremendously influenced by a lot of the research that he has done. He's currently University Distinguished Professor of Electrical Engineering and Computer Science at the University of Tennessee at Knoxville. He also holds a number of other positions, including Director of the Innovative Computing Lab, Distinguished Research Staff at Oak Ridge National Lab, Turing Fellow at University of Manchester, appointments at Moscow State University, Rice University, Texas A&M. So a lot of different positions. His work has been on numerical techniques, parallel computing, advanced architectures. Almost every HPC system today runs software that has been influenced by Jack's work, including BLAS and LAPAC and ScaleAPAC and MPI and PVM, and I could go on. He's received a large number of awards, including the IEEE Sid Fernbach Award, the Ken Kennedy Award from ACM and IEEE, the Charles Babbage Award, the TCSC Excellence in Scalable Computing Medal. He's fellow of AAAS, ACM, IEEE, SIAM, and a member of the National Academy for Engineering. And I could go on, but I don't want to take up the whole talk. So
just a little bit more, because my batteries are. My batteries just ran out of my pointer. Well, thank you very much for that very kind introduction. I'd like to keep this informal if we can, in the sense that if you have questions, ask the questions during the talk. It'll just make it more interesting for you and more interesting for me as well. So I want to talk about things related to architectural aware algorithms as we move on from the existing base that we have to peta. So we're at petascale now. So that's 10 to the 15 floating point operations per second, and we're going to go to exascale. So exascale is 10 to the 18. Okay, so I do work at the University of Tennessee, Knoxville. Oak Ridge is about 40 miles away from the campus, and I go there one day a week. And then occasionally I go to Manchester. It's about 4,000 miles from home. So I don't go there every week. So what I'd like to do is to overview high performance computing and then look at some implementations of some algorithms we've been working on. And they're an example of the kinds of things you have to be aware of, I guess, if you want to get, or if you want to extract high performance out of the systems that we have available. But first, let me start with this. So this was something that President Obama did on July 29th. So he has an executive order coming from the highest levels of government, which says they want to create a national strategic computing initiative. This is from the President of the United States. And that initiative has five themes. The first is to create systems that apply exaflops of computing power to exabytes of data. Now, I didn't say that, Obama said that. So he said exabytes and exaflops, so that was a good thing. He wants to keep the US in the forefront of high performance computing capabilities. He wants to improve application developers' productivity. He wants to make HPC readily available and establish hardware for future systems. So that's coming now, again, from the highest levels. We don't have to go to Congress and defend the case. The president said that. Now, having said that, there's no money associated with this. This is just an order that says these are important things. We should do them. And now somebody has to appropriate money in Congress in order to make that happen. Let's take a look at high-performance computing, let's say now, today. Petaflops. So there's systems. There are 81 systems. So we have this list of the 500 fastest computers. 81 of them have petaflop or better performance, so 81 systems. That's a pretty impressive number. We have three architectures that we see emerging. So three architectures, these perhaps are not too surprising. One architecture is based on commodity processors. So take a bunch of Intel processors, put them in a box, have an interconnect network, and that's going to be your base for a supercomputer. The second one is to take those commodity processors and add to it accelerators that boost the floating point performance. So think about putting in a GPU from NVIDIA or a coprocessor from Intel alongside of those commodity processors to boost performance. So we have a number of systems, 104 of that list of 500 computers, 104 use that architecture. And the third one is to have special lightweight processors. These are processors that specialize, let's say, in a certain thing. And they don't have all the complications that our commodity Xeon processors might have in terms of how the instructions are dealt with, look-aheads, multiple executions. They do things much more simply, and as a result of that can extract performance and maybe give us better power budget. So IBM Blue Genie architecture is like that. So IBM used to make supercomputers based on that chip. They no longer do. And that's an example. ARM is another example. So of course ARM has I would say probably the most processors in use today. They're in all of our cell phones and many other devices as well. And another example is Intel's coprocessor, Intel's Knight's Landing. So that's a specialized, very Xeon Phi is the way you should read that. Very large number of cores on the chip. Knight's Landing, they'll have 100 or more cores on a chip. Again, using x86 instructions, but having a much simpler architecture for the execution of those instructions, and able to, and because of that, keep the power budget and high rates of floating point arithmetic. We see interest growing in high performance computing, and it's worldwide. So, you know, there's efforts for high performance computing in the US, in the European Union, in Japan, in China. Korea has efforts, so a lot of efforts going there. And we see these markets growing, in the case of industry, becoming involved in high performance computing. So 50% of the top 500 machines, more than half of the machines are used in industry. So industry sort of gets this. It's a strategic advantage to have these computing devices. It gives them, it enables them to optimize their applications much better, produce better engines, better tires, better movies, and so on because of the use of high performance computing. And again, there are many efforts in different countries that are focused on developing the next level, the challenge that we have to develop exascale computing. Yes?
Do you know the breakdown within the industries? Like, for example, do you know what percentage is oil and gas, what percentage is military industrial complex, that sort of thing?
Absolutely, yeah. So there's a very complete breakdown based on sectors. And that information, I can't give it to you off the top of my head, but it's all contained in the website. So the Top 500 website will have that information. And you can get a pretty good idea of how it's being deployed and how things are actually changing over time, which is also sort of interesting. And Intel processors has the largest share. So if you take a look at those 500 computers again, Intel architecture is in 89%. That is, Intel's product is in 89% of the top 500 machines. AMD has another 4%. So x86 architecture really dominates this thing with 93% of the market. So that's sort of a stunning number, 93% used based on x86. And the others are made up from other companies. Fujitsu has their own architecture, and a few other scattered. IBM has their own architecture as well. Okay, so that's a picture of, in general, where we are today. Here's another glimpse of where we are and perhaps where we've been. So this is the top 500 list. This is the data that's contained in that we'll take a look at. So we're looking at the 500 most powerful systems. And we're going to measure the performance of those systems according to a benchmark. And we can argue if this is a good or a bad benchmark. I'm happy to have that argument. I'll probably be on your side. But this is the problem we're solving. AX equals B. So it's a linear system of equations. A is a dense matrix. And the ground rule will say you have to solve that problem using Gaussian elimination with partial pivoting. So all the results that we have for the past 23 years represent that benchmark, that specific algorithm implemented as best you can on your architecture. And you have to get the accuracy, you have to use 64-bit floating point arithmetic to do the computation. You have to actually run a program, you can't guess the solution. I'm going to give you the matrix. You tell me the size you want, I'm going to give you the matrix. You solve it using your implementation, and then I'm going to check to see that you got the right answer from that. So this list, and what we see is that as the size, the order of the matrix, so I give you A and B and you compute X with that method, and as we increase the matrix size, the performance will go up until we reach an asymptotic point. So this is a rate of execution, operations per second, and an operation in this context is an add or a multiply of 64-bit operations. And we want to look at your asymptotic performance. That's what we want to see in the report. So this list is updated twice a year. It's updated in November at the big supercomputing meeting. 10,000 of my closest friends attend. That will be held in Utah this year. And it's also, we also release it at a meeting that's held in Frankfurt, and now that's in June of this year. And that's, so that's the next time that the list will come out is in June. All the data is available. The most recent data is from November of 15. Okay, so here's a, if you will, a snapshot. We've been doing this for 24 years, right? So this has been going on for a long time. So this machine here, so what we're looking at is a plot of the fastest computer, the guy at the bottom of the list. So that's a bracket, if you will, for the 500 computers over time. And this orange thing is the sum of the 500 computers. So that's an artificial computation. Everything else is based on actually running the program. So this guy here is the fastest computer today, and that's at 34 petaflops. This is the slowest computer today. So if you want to enter the list, at least in November, it's 206 teraflops. So that, as you see, that always climbs, it never goes down. And sometimes, occasionally, there's a machine which is #1 for a long time. So that machine's been there 3 years, six times. And that shows it's a pretty powerful system, and that nobody can, no system has been built that outruns that system. And that's been true in the past, but this is the longest time that we've seen. So that's sort of the top 500 machines. So there's a lot of information that we can get out of this. What's the slope of that line? So you might think it relates to Moore's law. Moore's law says it should double every 18 months. The slope is doubling every 14 months. So it's accelerating Moore's law. Now, how's that possible? Well, it's because of parallel processing. We're using more and more processors every time, and that has a boost to it. These are expensive machines. So the guy at the top of the list cost about $200 million. So that's the price for the hardware only, and roughly. And after 6 or 8 years, it falls off the list. So if you want to stay in this game, you need to make an investment, a continuing investment in high-performance computing every 6 to 8 years. So you need to spend around $200 million for the hardware if you want to be #1 on this list. The guy at the bottom of the list, so that's the guy that just made it on the list, that was equal to the sum of all the machines back in 2001. So that's, again, that's an incredible story. Things are accelerating. You got this exponential effect going on, and it's really quite striking when it touches the things that we use. And this is probably an incredible situation we have today. My laptop, so it's a dual-core Intel Haswell processor, and I can run the benchmark. And when I run the benchmark, I get 70 gigaflops out of it. 70 gigaflops out of a laptop that I use basically to read email, right? And that's a stunning achievement in some sense. That would have been faster than the #1 machine back when we started in 1993. So that machine there in 1993 was a Thinking Machine CM5. It had 1,000 processors in it. And today we're walking around with devices that could run 10 hours on a battery. Yeah.
I used to work there.
You used to work there, right? So Los Alamos is where that machine is located. And, so my phone has an ARM processor in it. It can do floating point arithmetic pretty well. When I run, and there's an app for that. So you can download the app and run it on on your iPhone or iPad. And when I run it, I get 4 gigaflops on my phone. So this is something, it's got a battery 24 hours, I wear it on my hip, and I can get incredible rates of execution. That would have been one of the fastest machines back in 1997, which is, it would have been on the top 500 list in 1987. That performance of 4 gigaflops, you're probably not, well, maybe you are, you're not old enough to know what a Cray 2 is, but that's the performance of a Cray 2. Again, that's a stunning achievement in the technology and the rapid growth that we have. So that's an incredible story. That's the top 500 list. Again, that's for one benchmark, and we could argue if that's a good or a bad benchmark to use for these systems. It sort of looks like there's an inflection point going on right about there. We're not too sure what's happening. Some people think that's a signal about the end of Moore's law. I don't think so. I think it's more about investment that's been made in computing. So I think there was a problem. The economy was in crisis around this point, and I don't think the investment continued at the same level it had been with computing. As a result, things sort of dipped, and maybe we're on a different trajectory now as a result of that. We'll see how that pans out. This is a list of the top 10 computers. So this is number 1, and it's located at the National Supercomputing Center in Guangzhou. It's a computer that's called the Tianhe 2, and it's made by the National University for Defense Technology. So they're the integrators, right? So the integrators take commodity parts, put them together, and make a computer. So they did that. NUDT has had a long tradition of putting together supercomputers that have been used in China. And what they did is they took Xeon processors, commodity processors, 12-core Xeon chip, together with Xeon 5, the coprocessor, and they had their own custom interconnect. So they didn't use InfiniBand, they built their own. Built their own protocols, everything was built by themselves. It's faster than InfiniBand. It has better performance than bandwidth and latency numbers. And they ran MPI-based program out, of course, and that's in China. And that machine has 3 million cores in it. 3 million. That's a stunning number. So these machines are intended to be used at scale. Otherwise, you would buy smaller machines and a number of smaller machines to use to satisfy applications. So think about programming that machine with 3 million cores. Think about managing that level of concurrency. And by the way, this machine, in order to operate effectively, you need 4 threads of execution per core. So you have to maintain 12 million threads of execution in this application to get good performance. And they achieved 34% of peak, 34% of the theoretical peak. The theoretical, they achieved 34 petaflops, which is 62% of the theoretical peak. Yes?
3 million with the Xeon 5 or without?
So that's what I call cores. So that's cores from Xeon and cores from Xeon 5, right? So that's how that aggregate comes about. It's a heterogeneous system, absolutely. So that's what we're into today in terms of systems. I'll point out that on the machines that have NVIDIA Keplers, we're not counting CUDA cores, we're counting threads of execution that can, independent threads of execution that can flow. So instead of a CUDA core, you need to gang together 244 CUDA cores to make that one thread of execution, and that's managed by the hardware. Okay, so that's 3 million cores on the system, 62% of theoretical peak, and it uses roughly 18 megawatts under load. So 18 megawatts, that power number is about memory, CPU, and network. It doesn't include cooling. Cooling, you add another 30%. Right? So these machines are pretty, they use quite a bit of power. In the US, 1 megawatt year, running something that consumes 1 megawatt continuously for 1 year, you're going to be presented with a bill for $1 million. So a megawatt year is $1 million. And that machine, if you ran it for a year, here in the US anyway, it's about $18 million just to turn it on. Right? So that's an expensive thing. You got to be aware of power consumption for high performance computing. And then add 30% more for cooling. So again, that's a stunning number. You can't let that get out of control. And if we have time, we can talk about that. This is efficiency, if you will, flops per watt. So today we're about 2 gigaflops per watt. That's what that translates into. We got to be a lot better as we go forward in terms of that number efficiency, because this will, well, of course, things get out of control. At Oak Ridge, where I work, we have a computer that's made by Cray. Cray's the integrator. They take AMD parts and NVIDIA Kepler co-processors, GPUs, and they put them together along with their own network. So Cray's secret sauce these days, in the old days, Cray made processors. They don't do that anymore. They integrate stuff. So they take these processors and integrate them, but their secret sauce is their network, their interconnect, which they just sold to Intel. So Intel now has the rights to that. And we achieved 17.6 petaflops, about half of the performance of the #1 machine, half. And 65% is our percent of peak, and we get about half the power consumption of that machine as well. So, and then you go down the list here and you see various things. So the striking thing is numbers of cores that we're using on these systems. Again, to use them, you have to use them effectively, you'd have to multiply that by the number of threads of execution that you had achieved. The power consumption is up there as well. These machines are all over 2 megawatts in terms of power requirements. And the other thing is, we see these accelerators being used in a bunch of systems, and that'll be the future generation. So Intel's about to make public its Knight's Landing processor, which is their Xeon Phi, and this machine will be based on the follow-on, Knight's Hill, which has a slightly different character to it. It'll be self-hosted, as the word is. And these machines represent the last of the petaflop machines, and the next generation that's purchased will be exaflop. So sometime after a few years, 2 or 3 years, it's thought maybe exaflop machines will be ready to be purchased. And then there was this, last year about this time, the Department of Commerce in the US issued an order that's preventing Intel from selling parts to 4 places in China. Okay, and they cite concern about nuclear research being done on them. So on the list of sites that can no longer get these parts is the place that is the place that's running the supercomputer, the National Supercomputing Center in Guangzhou. So they have the #1 machine. Also, a machine which has a very powerful system, the Tianhe 1A, is in Tianjin, and it's prohibited from getting Intel parts. NUDT is no longer available to buy parts. They're the integrators, and the National Supercomputing Center in Shenzhen. That's where NUDT is located. They can't get it. So that hampers Intel from selling parts to the Chinese. But the Chinese say, okay, we'll make it ourselves. So what China did, this is taken from a talk that was given in June at the ISC meeting. Yutong Lu is in charge of the software architecture for the machine, and she presented a talk and described the old 2 machines and the new machine that they're building. So this is the Tianhe 2A. It's going to take these parts and it's going to replace the Xeon Phi with a Chinese-built accelerator. So they're building their own accelerator, which will be put on the boards, and it will speed things up to over 100 petaflops. So that machine could be ready in June, is the story that I'm hearing. So again, Xeon processors with Chinese accelerators. They've expanded the machine a little bit, not very much. They've enhanced their network as well to give it a boost in performance. And they've received more money from the Chinese government to do all this, of course. So the U.S. Commerce blockade is causing China to invest more in high-performance computing. So that was a strategic move. And this is a rough design of their accelerator, able to reach fairly high rates of execution and modest power consumptions associated with it. And we'll see how that works. It's easy to design something. How it actually works in practice involves software, and building software, as we know, is the place where we fall into problems. So this is looking at the 500 computers on this list. So this is representing 500 rectangles here. Each rectangle represents a computer. This is the biggest rectangle. So the size of the rectangle represents the power of that computer. So this is number 1 machine. These are number 2 and 3 machines, and you could probably scratch out the rest. US has 201 computers on this list. So of the 500 computers, 201 are in the US. Now that's the lowest number since we started collecting this data. So the US investment perhaps in high performance computing has not kept pace with other countries. China has 109. So that tripled the number that they had on the previous list. So that's a big investment that China is making in high performance computing. China had 0 computers in 2001. So no supercomputers according to this list in China. And then they made this consistent, steady investment to build out to a very large number. And again, this is the lowest point for U.S. systems. And you can see Japan, Germany, roughly about the same. UK and France about the same number of systems on the list. Well, you know the story as well as I do. Gordon Moore made this projection based on these 5 points, saying something about the devices or gates on a chip are going to double every 18 months as new chips emerge. And that's held true for a pretty long time. We see this Intel trend here with their processors just following that, doubling every 18 months. Some people say it's going to slow down, but I think it's still going to continue for a while, and that's going to be a great thing. That enhances everything. But the real secret sauce is not Moore's law; it's Dennard scaling. So Robert Dennard was a researcher at IBM, and he came up, he made claim to this. He said, look, we can scale things in a certain way. We can decrease the feature size by some factor and decrease the voltage by that same factor, and the number of transistors are going to increase by that factor squared. Right? So we got things on the chip growing at that rate. We can increase the clock speed by that same factor, and the energy consumption is exactly the same. So that's an incredible situation. We get twice the number of transistors, 40% faster, and 50% more efficient, right? And the way that touched me was I have an old machine, I get a new one. In the old days, I would take my application from the old machine and run it on the new machine, and it would run faster by this amount. And I was a happy guy. I didn't have to do anything, right? I just take my program and rerun it on this new machine. It's sped up by that factor. So this was the good old days. Unfortunately, Dennard scaling has some problems. As the feature size gets smaller, it leads to current leakage, and it causes the chip to heat up. So as we continue to reduce the feature size with Moore's law, we can't achieve the same things that Dennard was talking about in terms of increasing the performance, keeping the voltage, keeping the power the same. And we see that. So this is a scatter plot here of processors, looking at the cycle time of those processors and how that's changed over time. And it's quite apparent that something happened right around here. And that's when Dennard scaling broke down. That's when the feature size got too small and they couldn't continue with that enhancement in terms of building out or making the chip faster. So the chip is not faster, the cycle time is fixed, more gates are being put on the chip, and then the question becomes, what do you do with those gates? So Moore's law says, look, we got these, the Dennard scaling failed at this point. What we're going to do is we're going to take those gates and put them into cores. So we're making more cores on the chip itself. So that became 2 cores, 4 cores, 8 cores, 12 cores, 16 cores on a chip. Intel with its Xeon Phis have 60 cores on the chip. So those gates are being used to enhance that. The cycle time is not increasing though. So now when I get my new machine, it has more cores on it, more parallel processing, and I take my old program and run it, it doesn't run faster. So I'm not a happy guy. I have to do something. Okay, so let's talk about an experiment. I'm going to experiment with my laptop. So I have a machine which has a dual-core Intel Haswell processor. Haswell is rated at 2.3 gigahertz. And Intel says, well, that's the listed cycle time, but actually that processor can vary the frequency. up. It can change the frequency up. It's called turbo boost, and it can rise to a peak of 3.5 gigahertz. And it does that without your control. That's automatic. If the chip feels it can do it, it's not going to melt, burn up, or do something bad. It'll increase the frequency. And when I run something on my laptop, I see that happen. I see 3.5 gigahertz being achieved. So at 3.5 gigahertz, at 16 flops per cycle, I get, at 3.5 gigahertz, 16 flops per cycle, I end up with 56 gigaflops of theoretical peak performance out of one core. That's stunning, out of one core of that chip. So now I'm going to run some experiments. So I'm taking my laptop. It has 6 megabytes of cache, and I have 8 gigabytes of memory associated with it, main memory. And the transfer rate on that machine is 25 gigabytes per second. So that's the rate that it can go across the bus from the memory to the cache level, and then from the cache it will be accessed very rapidly. So I want to look at some operations under this model of my machine, and let's start out with some vector operations. We're going to do some simple things: take an inner product, or do a DAX feed. So a DAX feed says I'm going to take a scalar multiple of one vector and add it to another vector. So I've got this number of operations. I do this many flops, and I have to move some data around to accomplish that. Or a dot product, where we take multiply component-wise 2 vectors and then add up those numbers. Pardon? Absolutely. So doing those things at that rate utilizes Intel's vector operations on the chip. So that's how it's getting that rate of execution. So the Intel chips today actually execute vector instructions, or have the ability to access those AVX vector instructions that are on the chip. So we go back here just a few slides back. Let's see if I pointed out. So AVX is the instructions that do those floating point operations. AVX2 with a Haswell processor, and that's going to be enhanced again to AVX 512 with Skylake. So they can issue one instruction and do a large number of floating point operations simultaneously, and that'll be a vector operation. Okay, so let's take a look at this under this context. So what I'm going to do is I'm going to look at just these operations. So let's take a dot product. Dot product says we're going to take 2 vectors, multiply them together component-wise, and let's see the performance we get. And I'm going to make these vectors very large because I want to diminish the latency problem. So I've got a vector of length of 375,000 double precision words. And those vectors, I need 2 vectors. So one vector occupies 3 megabytes, 2 vectors fills up cache exactly, 6 megabytes for cache. So those 2 vectors come into cache and we're going to do some operations when they're there. The time to move the data across the bus, that's the speed of the bus, 6 megabytes of data, says it takes 0.23 milliseconds to move the data. So it's 2 vectors coming from memory into the part where I'm going to do the operations, 0.23 milliseconds. The time to do the floating point to end floating point operations at 56 gigaflops says it takes 0.01 milliseconds. So floating point operations are going to be free. You can overlap that with the data movement. So the total, so we're going to assume that we can do overlap. We're going to overlap communication and computation, and that says that the total time is going to be 0.23 milliseconds. 0.23 milliseconds gives us a rate of execution of 3.2 gigaflops. So that vector operation is running at 3.2 gigaflops. So if you have vector operations and you use the vector operation just as I did, that's the performance. This is the peak performance of the chip. So you're getting nowhere near the peak performance, order of magnitude and more from the peak performance. So this is a memory-bound operation. Data movement kills you in this operation. So there's a lot of mathematics that goes behind the scene here, which I don't have time to go into, which says if you use this thing as the right-hand side, you get a correction to the solution, but that's the way this algorithm works, and you can run this algorithm. So this is, again, an old algorithm that's been studied, and error bounds are provided. The newer trick is that you can do this by using selected precisions here. We're going to do the factorization in single precision, and that consumes order n cubed floating point operations. We're going to compute a solution with that, again using single precision and order n squared operations. Then this operation here must be computed at double precision. So everything has to now run at double precision. The residual has a double precision accurate solution. And then we compute this correction in single precision. The correction is the thing we're going to add into this fully double precision version of the solution. So we're going to add this in. Think of it as this. We've got very accurate high order bits for x. It's the low order bits that have to be corrected. And that's what z is giving us, the low order bits for x. And then we compute a residual and carry on. So the single precision is dominated by n cubed. Everything else is order n squared or less. So what happens, what you can prove that when this converges, or if this converges, that you will converge to the solution that's as accurate as the full precision results, 16-bit, 64-bit results. So it's as accurate if it converges. So what's the catch? Well, the catch is that it may not converge. It may not converge because the conditioning of the problem, the ill conditioning of the problem, is such that we don't have one digit of accuracy in x. If we don't have one digit, I can't correct. I have nothing to go on, is the way to think of that. So the condition number has to be less than 10 to the 8th. That says I've got one digit at least. If it's 10 to the 8th, it starts to have problems. That's the ill conditioning coming in. And the other thing is I need a copy of the original matrix in single precision, because that residual has to have the original matrix, the original data, to get an accuracy to the original problem. So I need 1.5 times the storage. I need storage for computing the residual, and I need storage for doing the factorization. This factorization is done in single precision, so that's half of the storage, I'll say. So I need 1.5 times the storage that I would have if I ran the algorithm in double precision. So how does it work? So this is a graph without using iterative refinement. It says this is the performance we see in double precision on this system, and this is the performance we see in single precision on this system. Again, no fancy algorithm, just run the straightforward algorithm. So this is running on an Intel platform which has Intel 2 8-core chips, and then it's running with a Kepler 20C GPU. And that's the performance level we see. So these are gigaflops here. This is not gigaflops. This is, it's 1.6. Yeah, this is gigaflops. Okay. So that's the rate of execution that we see out of that. I probably exhausted my time, but let me just describe some issues that I find challenging, exciting is a better way to say that. So we're looking for algorithms that reduce synchronization. We have to come up with algorithms that break the fork join model. Loop level parallelism won't make it on the machines that are coming down the road. We have to think about reducing communication. Minimizing data movement is going to be critical. Data movement's the most costly thing, I'll say, in terms of our numerical computations. So we should think about methods which have a lower bound on communications and implementing them. We want to be able to use or exploit mixed precision when we can. That is, relying on single precision for part of the computation, switching at some point to double precision to enhance the accuracy. And some iterative methods you can do that as well. Start out in a short precision and then move to long precision as you come closer to convergence. We want to look at auto-tuning. These are terribly complex systems, and I can't leave it to the user to adjust all the knobs and dials. I want to put that into the software, so the software is able to figure out something dynamically and then run with that dynamical configuration in place to avoid having the user to do it. Fault resilience is going to be, I think, an important topic. That is being able to transition past process failures and even detecting silent failures that happen, bit flips that might occur, and design that into the software. Today's model for MPI is such that if a process fails, the application falls over. So we have to correct that, and that requires the standard to be changed to allow for issues of fault tolerance. We're working with a number of people to come up with a sensible way to put that in place so the standard and effectively we would give life to the algorithms that are implemented through that. This is sort of an interesting thing, reproducibility. So most people think that if I run my application on a computer and if I come back tomorrow and run the same application with the same data on the same computer, I'm going to get the same results. That isn't true, right? So that went out the window with parallel processing. So if you think about, think about this vector, think about a dot product. We're going to take the component-wise multiplying elements and then do a reduction down to one number. I can't predict how that reduction is going to occur, the order in which that reduction is going to occur in parallel. And because I can't get that order fixed in general, I'm going to come up with different bitwise numerical results. It's if I add things from largest to smallest, I get a different number if I add things smallest to largest. You can think of it like that. And that doesn't bother me. I'm a numerical guy. I have error bounds for my applications. The fact that I get a different result today and tomorrow, that's okay. Some people insist on it though. They say, I've got to get the same results, right? Guys designing reactors. MathWorks, we have a large discussion with the guys who do MATLAB. They want the users, they claim, demand the same results today and tomorrow. Okay. I can do it, but it's going to cost. It's going to cost. And to be honest, if I'm debugging a program, I got to get the same answer today and tomorrow, otherwise I won't know where the bug actually exists. So it's not an unreasonable thing to require. But it requires careful thought and implementing it so the performance penalty is not too high. So that's basically it. I've talked about these things. Parallelism, it's growing to billion-way parallelism in the future with exascale machines. We have hybrid systems today that cause some issues because of the way the hybrid nature of the architectures are put together. Fault tolerance is going to be a big deal. Today's machines, we see a large number of failures or failures that can take the machine down. The power consumption, if built on today's technology, we have to get better. We have to get better efficiency. We can't stay at 2 gigaflops per watt. The machines that we build in the future have to be more like 50 gigaflops per watt, and that's going to be a struggle to get to. But there are signs that we can actually get to that point. So we need to, come up with new approaches and technologies to reach exascale and to be successful on the machines that are coming down the line. So with that, I'll end, and thank you for your attention. If there's any questions, if we have time, I'd be happy to answer.